the following expressions. And sigma theta okay. And so this is true if where K is the yield stress in shear. Okay, please try to follow what I mean to say by this. Uh, so it's not as if uh, if the inner radius starts yielding, or let's say plastic deformation has reached a certain radius of C. For the rest of the geometry, we could write this expression. No, this expression can only be written when the entire geometry is elastic. Okay. For example, we could write tau equals tau max uh, r divided by r0, or where tau max being 16t by, okay, 2t by pi r cube, r0 cube. Okay, so this expression, much like this, the above two expressions, can only be written when the entire cross section is uh, elastic. Okay. Now, of course, as compared to torsion and elastoplastic bending, uh, plastic deformation in thick cylinder, okay, is as contrary to the other two cases. It starts from inside and then goes towards outside. Okay, so we have a plastic core and an elastic shell. Now, uh, at the initiation of welding, that is, at the initiation of plastic deformation, so this quantity evaluated at A should be twice K. Now, how much is this quantity? This quantity, as we can see, is P times, actually, it is going to be twice B squared by R squared. So Please check sigma r plus sigma theta is twice p b squared by a squared minus 1, and this quantity is twice a, which is a constant. Constant with reference to what? Constant with reference to radius. It's not changing with radius. Okay, but such is not the case when you take the difference between the two. So you have this expression, let's call it p prime, which is, okay, of course we can cancel the 2's from either side, and then we have the following expression. Okay, this quantity needs to be evaluated at a, so it is k times a squared b squared times b squared divided by a squared minus 1, or in other words 1 minus a squared by b squared. Now this is a very special expression. If you think about it, uh, this part is elastic and this part is plastic. Okay, and the stress strain modulation is elastic, perfectly plastic. Now if you are anywhere over here, okay, so you have already undergone quite a bit of plastic deformation, but this point right here is a very special case. This point right here, that is the yielding point, it belongs to both the sides of the curve. It's kind of the bifurcation point, much like buckling. So the elastic equations are valid, and so are the plastic equations. Okay, and actually that's how we got the expression for p prime. So this is the plastic part of the equation, and these two are coming from elasticity. And both of these conditions are valid at yielding, okay, and only at yielding. At any arbitrary amount of plastic strain, that would not be valid. Okay, although the material is still going through plastic deformation, that expression is not going to be valid. Okay, now imagine, so all of this you are supposed to recall because all of this was done in the previous class. Say if the size of the plastic core is C. Consider the case that the size of the plastic core is C. Then let's call it P star. Okay, we'll have the following expression. So that means at C, so the stress state may be different in different locations. For example, over here it is elastic, and over here the plastic deformations are going on. But C is that radius where both the equations are valid. That means any point that is at C away from the center is going through yielding. Okay, and of course, as the pressure changes, that point also shifts towards the circumference. That means that C gradually increases to circumference. So this is the expression. Okay, for the pressure at C. Okay, which would mean that if R is greater than C, that means in the elastic domain, So this is the elastic part, and this is the plastic part. Okay, so that means you are going through elastic deformation. So over here, your sigma r is going to be P star. So this equation, this very equation only comes into play, okay, when you have yielding. Okay, so if you are within the elastic domain, okay, so this equation will be valid. B squared divided by r squared minus 1 divided by b squared by c squared minus 1. So C takes the place of A, because now the elastic region is between B and C, or rather C and B. And that means we are treating as if the elastic region, which starts from C, as a thick cylinder on its own, okay, which is deforming elastically. And in that, this P star acts as an internal pressure, okay. And this is the expression for the sigma theta, which would be, sorry, this one is minus. So this quantity would be, as you can expect, this quantity. And you can check by substituting C over here that you get sigma r equals minus P. Okay. Now, let us look at how the stress state changes in the plastic domain. Okay, that is, by stress state I mean different stress components, as in the sigma r and sigma theta. Okay, so for r between C and A, the difference between sigma theta and sigma r must be twice k. Okay, so all of this is coming from, as you can recall, from maximum shear stress theory. Okay, we established that sigma theta is the highest principal stress and sigma r is the lowest principal stress. Sigma z comes in between in every possible scenario, and there are no shear stresses. So essentially, the r theta z becomes the principal coordinates. Now, let's go back to the equilibrium equation. Which says sigma r prime plus sigma r minus sigma theta divided by r equals 0. And if I substitute that, then I get this expression, sigma r prime equals twice k divided by r, or d sigma r equals k times twice dr divided by r. On, so this quantity right here is dr by r is actually twice ln r. Okay, and by using the principles of logarithm, this makes it r squared. Okay, so now let us try to integrate both of these quantities. So yeah, sorry, actually it is d ln of r squared. So let's now integrate it between uh, any r and c. If we do that, then we have sigma r at c minus sigma r, and that way we also have k of ln c squared divided by r squared. Okay, now this quantity, as we know, is this p star minus p star, which is k 1 minus c squared divided by b squared, which gives us the following expression for sigma r, which is minus k times 1 minus c squared by b squared plus ln of c squared by r squared. Can you check if this expression is correct? Is this correct expression?
Yes, sir.
Okay. Now, can you calculate sigma theta? How do you propose we calculate sigma theta? We would use this equation, and therefore sigma theta is twice k plus sigma r. And what is the expression for sigma theta then?
k into 1 plus c square by b square minus ln c square by r square.
This one, right?
Yes, sir.
If you look at your textbook, this expression is given as plus, which is incorrect. So now what we would do? Now you would satisfy that, you see, we want to have a relationship established between the size of the plastic core and the applied pressure. Okay, if I know the size of the plastic core, and if I know the yield stress, then I can determine the stress anywhere within the plastic zone as well as within the elastic zone. Okay, because you see, by knowing C and K, I can determine what is P star, and then from that I can get the sigma r and sigma theta of sigma r and sigma theta even in the elastic zone. So so these are the set of equations. Okay, so once I know the value of C, these are the equations that I can use in the plastic zone. Okay, and these are the equations that I can use in the elastic zone. Okay, but the question is, what is the value of C for an applied pressure P greater than P prime? Okay, or in other words, what is the value of P required to cause, okay, this size of the plastic core? Actually, the second question is easier to answer because of the fact that this is how the relationship works. Okay, so sigma r at A must be minus P, which when equated to the expression of sigma r from the plastic zone and substituting for A in place of R, this is what we get. Sorry, the R must be replaced with A, right? Okay. So if you know the internal radius and the external radius, or inner radius or an outer radius, sorry, and if you know the size of the plastic core, then you can figure out P, the pressure required to cause that size of the plastic core. Okay. Now, if you want to figure out the size of the plastic core for a given pressure, then that is an iterative method. Okay. Then you can write the expression something like this. Define this quantity as okay, sorry, this is also minus, so P minus K times 1 minus C squared B squared plus ln of C squared by A squared. Okay, so all of this you can write. Okay, and let's say you take an initial guess of C0, which could be anywhere between A and B, and you substitute that value in the expression of F. If it falls below, if F is less than certain tolerance, let's say approximately 1 in 100,000 of the P prime maybe. Okay, so if it's below this tolerance, then exit. You have calculated the value of C correctly. Else, calculate F prime, not F prime, let's call it. Else calculate del F del C. Take the derivative of F with respect to C, which would tell you that this is twice Kc divided by B squared minus 2 by C, twice K by C. Okay, so and then you can perform analytic iterations. So Cn plus 1 iteration is C minus Cn minus F divided by F prime evaluated at Cn. That means the value of C at nth iteration can be used to calculate both F and F prime, and then you can update C for the next iteration using this formula. Okay, using Newton-Raphson iterations. Okay, the reason I chose to do that, okay, because I'm about to show you some simulation that I made, okay, of the variation of pressure, which incorporates this calculation. So basically, I'm only changing the pressure and letting the things happen. Okay. Acha, letting the things happen. I'm not assuming that the score size must be such and then calculating the pressure. I'm just trying to get C with respect to the values of P. Okay. And how am I doing so? Is through this set of iterations. Okay. And if you do NR iterations, you know that NR iterations are really fast. Probably a couple of iterations will be good enough for you to land reasonable, uh, mm, closeness to the tolerance. Okay. So when today I give you an assignment, okay, so I'll try to give it the way this way that you get to do both. Okay. So far we have only been trying to do this, having the size of the core, whether elastic or plastic, and then trying to get the required torque, required uh, point force, or required pressure. Okay. But we should be in a position to do the reverse as well, because the reverse would be more important. So let's say if I'm changing P uniformly with time, or at a constant rate with time, then how is C changing? Okay, so that we can answer using this set of equations. Okay, uh, now let's look at some of the expressions. So this is the expression for P, right? K times 1 minus C squared divided by B squared plus ln of C squared by A squared. Okay. Acha, now check, if I take C equals A, what is the value of P that I get? If I take C equals A, what value of P do I get?
K into 1 minus C square by B square.
So this term becomes 0, right? Because C squared divided by A squared, if C equals A, becomes 1, and ln 1 is 0. So essentially that would give us P equals P prime. Okay. And that way we know that our formulation is consistent. What did you say? K times 1 minus C squared by B squared. If you take C equals
A square by B square. A square by B square.
Sorry?
K into 1 minus A square by B square.
A squared by B squared. If
Yes.
C equals A, then that P is supposed to be K times 1 minus A squared by B squared. Okay. Which is actually P prime. Now, can you tell me what is the maximum load bearing capacity of the thick cylinder or the thick walled tube? By maximum load bearing capacity in this reference, I mean, what is the maximum pressure that you can apply? And what is the answer?
K into ln B square by A square.
Yes. So that means C equals B. Once the entire cross section has become plastic, and in plasticity you do not have any hardening, okay, so no further load can be added, and this is how you get the value. C equals B. So you get the value P equals K times 1 minus B squared divided by B squared, which is 1. Then these two also cancel out, plus ln of B squared divided by A squared. Okay. K times ln of B squared divided by A squared. Okay. Let's call it P double prime. Okay. It is that critical pressure beyond which you cannot apply to that thick wall tube. Okay. Now, P prime is this quantity, right? K times 1 minus A squared divided by B squared, and P double prime is K times ln of B squared divided by A squared. Can you tell me which quantity is going to have higher value? 1 minus A squared by B squared or ln of B squared by A squared? Which quantity has the higher value?
P double prime.
P double prime. And how do you know that? It's not obvious from these two expressions. That's for sure. You know that because it has to be. Because it has to be. P double prime has to be greater than P prime. Because it's by changing this pressure from P prime to P double prime, you have made the cross section having no plastic region. That means the value of C equals A to be entirely a plastic region, that is C equals B. Okay, but it's not quite obvious from these two expressions. Unlike the previous examples, here it is not obvious. Okay. Now take A by B equals 0.5. Okay. Now can you tell me how much is A squared by B squared? Of course, this one is really simple. This is going to be
0.75.
0.75. But what about this? Can you calculate
Minus
this?
1 point.
It's negative.
Sorry?
Minus 1.38. Minus 1.38.
Minus 1.38. Acha, P prime just turned out to be minus K this quantity, right?
স্যার মাইনাস হবে না, ওটা শুধু 1.38 হবে।
1.38. Yes, of course it is going to be positive. Ln of B squared by A squared. Yes, because sorry, yes, B squared by A squared. So it's because B is greater than A. So basically you are taking log with respect to any arbitrary base, let's say base A can be 10 or anything, of 4, because B by A is 2, square of that would be 4, with respect to this quantity, and then dividing, so that basically gives you ln of 4, right? So same base A, and then you are getting the log of the Euler number itself. Okay, and in mathematics, there are so many equations and so many numbers named after Euler. If if you do not mention the second scientist in most cases who independently discovered that, okay, then it becomes confusing. But still, this is Euler number. So the value of this quantity is 2.71828. Okay, 1828 and so on. So basically, this is smaller than 4. So you can expect the division results into a number higher than 1. Anyways, so for 0.5 this works. Okay, now I need you to check also this. If a by b equals 0.9, okay, and this time the thick cylinder is not as much thick. You can see the two radii, the inner and the outer radii, are very close to one another. So it is going to the domains of thin cylinder. Okay. So if a by b equals 0.9, can you check how much is this value?
Point 0.19.
0.19, right? Okay.
Yes.
And what about this quantity?
Point 0.21.
0.21. The point being, you see how close these two values are? What does that mean? This is the pressure at which nowhere in the cross section there is plastic deformation. It's just about to start at the inner radius. And this is the pressure at which the entire cross section has become plastic. Okay. And everywhere plastic deformation is taking place. Okay. And that window is only 5% of the average value, only 10% of the average value, which is 0.2. Whereas in this case, it's pretty wide. If you have a thick cylinder going from plastic deformation starting at the inner radius to the entire cross section becoming plastic, that's quite the window of pressure. Okay, let's say K is 100 MPa is too much. Let's say K is 80 MPa. Then this is 60 MPa, P prime, and P double prime is around 110 MPa, maybe. And let's take that same 80 MPa over here. Of course, it's a thin cylinder, so the pressure required would be smaller. Okay, but that is just somewhere around 15.5 to 17 MPa. That is the window of pressure by which the entire cross section would be plastic. Okay. So yeah, so these are the things that are important. Now in either case, we saw that obviously this quantity is greater than this quantity. But can we definitively prove that the second expression is going to be higher than the first expression? Now let's look at ln of b squared divided by a squared, which can be thought of 1 plus b squared minus a squared divided by a squared. No, I don't. I think I cannot use this expression. What expression do I have to use? Okay, okay, understood. So I can write this expression to be minus of ln of a squared by b squared. And then I can write this to be minus ln of 1 minus a squared minus b squared minus 1, which is minus ln of 1 plus no, sorry. Okay. 1 plus a squared b squared minus 1. Okay. So yes, okay. Now now this logarithm ln of 1 plus x is always less than x, irrespective of what sign x has, what value x is. Because you see, if I expand ln of x, that is x minus x squared divided by 2 plus so on. So the next significant term is x squared, and that is always a positive quantity irrespective of the sign of x. Okay, so if x is a negative quantity, which is in this case because b is greater than a, so the ln of that quantity becomes even more negative. Because x is negative, then this quantity is definitely negative. If x is positive, then also this being negative, this quantity right here is actually smaller than x. This is always smaller than x. That means this quantity is greater than a squared, because this one comes with a negative sign. Sorry. Yeah, mistake. So that means ln of 1 plus a squared b squared minus 1 is smaller than a squared b squared minus 1. And now if I put negative sign on either side, so this quantity is actually greater than this quantity, which is 1 minus a squared divided by b squared, which goes to show that this quantity ln of b squared by a squared is actually greater than 1 minus a squared by b squared. Okay, it just so happens if this quantity is very close to 1, or rather this quantity is very close to 0, okay, the difference between the two quantities, the two sides, are actually really small. Okay. Acha. So the next thing that we would do is talk about residual stresses. Okay. So so far you have taken the pressure to this value, okay, for an arbitrary to cause a plastic core of size C has formed by pressure P equals K times 1 minus C squared divided by B squared plus ln of C squared by A squared. Did I write this correctly?
Yes, sir.
Okay.
Yes.
And stress states, or rather stress distribution, within the elastic zone is this quantity. First of all, P star is K times 1 minus C squared by B squared, and then sigma R is P star minus P star B squared divided by R squared minus 1 divided by B squared by C squared minus 1, and sigma theta equals P star times B squared by R squared plus 1, and in the denominator B squared by C squared minus 1. Okay. And this is the stress state when R is between A and C, that is within the plastic zone. Okay, so so this portion is elastic zone, and then in the plastic zone you have the following expressions: sigma R equals K times 1 minus, actually minus K times 1 minus C squared by B squared plus ln of C squared by R squared. I guess I'm writing the correct expression. And sigma theta is K 1 plus C squared by B squared minus ln of C squared by R squared. Okay. So these are the expressions. Okay. So we need to have the stress state. So before unloading. So we are somewhere over here. Okay. So in the elastic zone, we are somewhere over here, and we'll simply doing elastic unloading. Okay. And that is to say, we'll not be reducing the stresses in the elastic domain by the same amount as these two. Okay, that would be some other stress. Okay, and which could make us land up in the compressive side. Okay. So the loading and unloading for each zone is not by the same amount, and that's why we develop residual stress. and even in the plastic zone, if you have raised this material to these two stresses, you would be unloading by different stress. Okay, and possibly in the plastic zone, you would end up being somewhere in the tensile side. Okay, if the original loading was in tension. So now, what would be the unloading stresses? That is the stress that would be unloaded. Okay, that is that will depend on the maximum pressure, okay, or the pressure you raised the material to. You are unloading the pressure, that is constant. So this pressure now becomes zero. So you increase the pressure from 0 to P, okay, and let's say somewhere over here you encountered P prime where the plasticity was initiated in the cross section, okay, and now you are somewhere over here at P, and then you are trying to unload over time, and by the time you unload, the pressure becomes zero, but the stresses may not be zero. Actually, the stresses won't be, and that's why you have the residual stresses. So for that, we'll calculate the delta sigma r, which would be unloaded, and delta sigma theta, which would be unloaded. And the expressions are really simple. So this is the, so by P, I mean this P, that P that is required to cause a given plastic core, okay, given diameter radius of the plastic core, okay. So you calculate that P, and that P would be now unloaded, and therefore this much stress should be subtracted. So and this is what would be subtracted from this expression as well as from the expression in the plastic zone. Is just that the R values, okay, would be different for the elastic and the plastic zone. So try to get the expressions for the sigma R after unloading. Basically calculate the residual sigma R, which is sigma R from elastic and the plastic zone, okay. So the expression would be different in the elastic zone, and the expression would be different in the plastic zone. For each zone, take the corresponding value of sigma R and subtract delta sigma R, which needs to be unloaded. Get the expressions for the residual stresses, sigma R, and then sigma theta. So what is the expression for sigma R residual?
minus p star into b square by r square minus 1 divided by b square minus c b square divided by c square minus 1 plus p into b square by r square minus 1 divided by
Yes, substitute
b
the
square
expression
minus
for
b
p in
square by a
that.
square minus 1.
No, so the part where you are mentioning p, substitute the expression for p in that. Okay, so that would be the expression for the residual stress. And similarly, you can get the expression for the uh, residual sigma theta. Okay, so the expression for sigma theta, or the unloading sigma theta, would be this quantity, as if you are loading or unloading that entire pressure, which took us from 0 to p prime, and then over here where you have a plastic core and an elastic shell. So if that entire pressure could be applied within the limits of elasticity, so what would be the stress distribution that is being unloaded? Okay, so this should be subtracted from each zone to get the expressions for the residual stresses. Okay, and substitute for the expression for P, then you have the complete expression. Okay.
Okay.
Okay. So you can get the expressions for the residual stresses. Meanwhile, I'll give you a couple of assignments. Number one, uh, so let's say inner radius is 100 mm, and the outer radius is 110 mm. Okay, or should I take something else? 120 mm. Okay. So and yield stress in yield stress in shear is 80 megapascal. Okay, so you can immediately calculate. So this is basically K. You can immediately calculate what is the maximum pressure or P double prime that you can apply, which would be twice tau y ln of B by A. Okay, so I took B squared by A square and made it twice ln of B by A. Okay, so plot C as a function of as a function, let's say, C of P as pressure changes. So this is the size of the plastic core as pressure changes from. Oh, you also know that P prime, that is the yield pressure. So first time there is plastic deformation starting. So the yielding occurs at R equals A, and that is tau y times 1 minus A squared by B squared. Okay. So as pressure changes from P prime to P double prime in, let's say, 10 steps. So take 10 values between P prime to P double prime, both inclusive, and calculate C using Newton-Raphson method. Okay, so the method that we just discussed, and then make a plot of this is not how they should be. Let's say this is P prime and this is P double prime, and let's say this is A and this is B, and you are probably going to get a plot like this. Okay, so that is assignment number 1. So now let's say this is R average, which is A plus B by 2. So second part of the question, same question, calculate residual stresses at R average for each case. So there will be 10 steps. So for each step, you also need to make a calculation of the residual stresses of sigma and sigma theta. And maybe you can even plot them. Okay. But I want the residual stress at a particular location. Okay. So the point is you will have to calculate the sigma and sigma theta, okay, while loading, and then how much would be unloaded, okay, how much is the unloading stress, and then make a subtraction of that. Okay, so in in the first part, when C value would be smaller than, so this I'm plotting C, right, in this axis. So as long as C is smaller than R average, okay, you would probably develop one type of residual stress, okay, positive or negative. Then once it goes past R average, you will be developing other type of residual stress. Okay, this time sign changed. Okay. So I need you to do both the calculations. Okay, so with that part done, okay. So is it clear for you whatever has been discussed today? do you think you'd be able to solve problems if I give you such questions for assignment, or if you get some such questions in the semester?
Yes, sir. Perfect.
Okay, okay.
So
But the
এটা কি স্যার
class
এক্সেলে করতে হবে না ম্যাটল্যাবে?
তুমি যখন প্লটটা তুমি যাতে খুশি করতে পারো, আমার কোনো অসুবিধা নেই। ওকে, but if you can write a program to do NR iterations, okay, in MATLAB, that is excellent. If you cannot write a program for calculating in MATLAB, if you cannot write a program to do the NR iterations, okay, if you do have to do it by hand, then you'll have to do it by hand. Okay, so so either way, either by writing a program that which would be much simpler, or by writing by hand, okay, either way is fine for me. But in the end, you'll have to generate that plot. Okay, the plot has to be done in the computer, either from Excel or from MATLAB. Okay, Achha. So I want to show you another thing. Okay, so this is the plot of the radial and the tangential stresses, and here it mentions what pressure is being applied. Okay, so and this is the radius, and I took the inner radius to be half of outer radius, which is quite impractical in real life situation. But the reason I did so was for you to visualize. You'll be having quite a bit of x-axis to visualize how the stress is changing. Okay, and one more thing, you see the radial stress is always negative. Okay, it is 0 at the outer radius. Okay, it is maximum at the inner radius, but it is always negative. Okay, so instead of I don't know, for some reason I chose not to have any negative values in my plot. So for some reason I took it to be the absolute value. By that I mean that when you see the plots in the elastic domain, initially the as p rises from 0 to p prime, okay, that is when the plasticity is initiated at A. So this line, this black line in the middle is A, and this one right here is B. Okay, so until then, as long as P is below P prime, you have only elastic deformation. And in elastic deformation, you would expect the sum of the radial stress and the tangential stress should be same. But because I took the absolute value of sigma r, what you would see that the difference between the two lines remains same across the radius. It's not with changing pressure that the difference remains same. It's along the radius for a given pressure that it remains same. Okay, and even when the plasticity is initiated, okay, you'd see the reverse. Then you would see, instead of having the difference being a constant, you would see the sum being a constant. Okay, so those are the heads up. And now let's watch this video. You see, at any given pressure, and right now we are below P prime. How do I know we are below P prime? I have also made another line representing C. and that line we do not see within the cross section right now. Okay, so that means that line C isn't there. That means plastic deformation has not started. So do you see the difference between the two lines are same? Now imagine this red line right here, which goes to 0 at the outer radius. This is in reverse. Okay, then actually the sum of the red curve and the blue curve would be same. Right now what you are seeing is that the difference is the same. Okay, because I took the absolute value. Okay. Okay, and that just goes on for a while. Okay, now let's say about 75 MPa is when you first encountered plasticity, and then this another radius C is now visible. Okay, and what is happening, inside C the stresses are now changing differently as compared to outside of C. And inside C, if I were to take the correct sign of sigma r, the difference between sigma r and sigma theta would be same. But because I have taken the absolute value, their sum is actually remains constant for a given pressure. So the starting value of sigma r was 75 MPa. Okay. So please remember, how did we get that 75? I took the ratio A by B equal 0.5, and from that we got that the P prime value is 0.75. And that means you would expect that by the time we reach, okay, so you see I took tau y equal 100 MPa. So by the time we reach B, okay, when C becomes B, then we would expect that the stress right here is 138 MPa. According to your calculation, which is ln of b square by a square. Okay, so it is already 131, 132. 1 second. Okay, so it has gone 138. Now, so the program was so written, once I go the maximum value. Okay, so now you see that the entire cross section has become plastic. Okay, and this cross representation graphically basically indicates that the sum of the two curves is same. For example, this middle line right here, 100 MPa, okay, is is the is actually twice the sum of both the quantities. Okay, it's because I, instead of sigma r, I took the absolute value, which is minus sigma r. So if sigma theta minus sigma r equals twice k, then sigma theta plus absolute value of sigma r is twice k, which is 100 times 2. So if the blue curve goes 40 MPa below 100 MPa, red curve goes above 40 MPa, goes 40 MPa above 100 MPa. Okay, so that way the sum remains constant because I took the absolute value of sigma r. Okay, and now I am reducing the pressure. So now I'll be developing residual stress. But you see, in this particular example, I have gone up to P double prime, that is the maximum load bearing capacity, and then started unloading. The point being that my entire cross section has gone through plastic deformation, and I don't have separate elastic and the plastic zones where the unloading takes place and different set of residual stresses. Okay, so I only have the plastic zone. Okay, and I am unloading from that maximum pressure P double prime. So my unloading pressure or unloading stresses would be calculated based on P double prime. Okay, so you see, it's what it basically showing is that the different phases of unloading, how much is the stress. Once I have done complete unloading, it doesn't seem like it is going to happen. But once I have completely unloaded, there is no internal pressure, right? And then I would expect the sigma r to go back to 0 over here as well. So sigma r should be 0 at the minimum value, that is r equal a, and it should also be 0 because of the boundary condition at r equal b. Just check that. Okay, so so this is the residual stress you can expect. Okay, uh, so this is the residual stress that you can expect once you are unloading from the P double prime. But if you were to unload from any other pressure, anywhere between P prime to P double prime, you'd get different type of residual stress. And of course, if the unloading takes place at a stress below P prime, there would be no residual stress, because then the entire deformation has happened elastically. So elastic loading and elastic unloading, which means that each point within the material would be unloaded by the same amount of stress that it reached while in the loading phase. Okay, so there will be no residual stress, but such is not the case with plasticity. Okay. Okay, so I'm done with whatever I needed to show. But you can only tell me that if this makes things a little simpler or a little easy for you to understand. Okay, so we'll meet on next Monday, and on next Monday we would be talking about instabilities in plasticity.
Okay,
So
sir.
one more thing, the most familiar example of plastic deformation is plastic deformation in tensile loading, and we did cover bending. Okay, now all of you who did some applied mechanics laboratory class in your undergrads might have done some tensile test, some torsion test, some bending test. Okay, now you can imagine that the bending and the torsion we already covered in the elastoplastic deformation. Why did we not cover the tensile deformation? Or can we experience residual stress in tension? Okay. Now, let that be your third assignment question. Can there be residual stress in in a tensile loading and unloading? Okay. The assumptions here is that the member is quite slender. The loading, the tensile loading are being applied far from the region where we are, concentrating. And number three is the the cross section is so narrow compared to its length, then the stress can be assumed to be uniform across the section. Okay, which means there is no variation of stress across the section. The section everywhere the stress is same, which is F by A. Okay, unlike bending, torsion, and thick cylinder, there is no stress variation across the section. Okay, and with that no stress variation across the section, can we experience residual stress if the situation is ideal? Okay, so that is your third assignment question. Okay, so we'll meet on Monday.
Okay, sir.